Very well. Enough of functions, at least for, no, enough of patterns. I go back to the lists today and then into maps. So we looked at the list, I think, already some time ago. What I want to do is to jump straight to matrices. I think we looked at this also. This is a way of generating two-dimensional arrays in Mathematica. So we have a table, and we have not one but two iterators. So the rules for one iterator apply, of course, to two iterators as well. Here, so I have iterators with just one, actually two arguments, iterators with 4 arguments. I mean, you guys have seen all of these already, so I can just go fast and jump to matrices. A matrix in Mathematica is defined by rows, and it has the constraint that each row is a list with the same number of elements. What is the difference between MATLAB's definition and this definition? In MATLAB, you must have, it's the same, you must have lists of equal length in order to have a matrix. But in Mathematica, if these lists are not of the same length, the definition is still perfectly fine. It's just that you don't get a matrix. You get a list of lists. So let's evaluate. I say the proper tool to visualize matrices is matrix form. Okay, it formats it nicely. I'm considering assigning the exercise of extending matrix form to draw the grid and to draw sub-matrices. I have to think about it. Maybe it's not so useful. All right, you can have, of course, a symbolic matrices. Look at the contents of this guy here. I put the subscripts I and j, and I let the subscripts run, and so I get a symbolic matrix. This is a numeric matrix. Okay. Okay, this is the same part. Symbolic numbers. Okay. First element of a matrix is a row. We saw this already. Because a matrix is defined as a list of lists, so the first entry is the top row. This is, we're counting backwards. Okay, we have seen all of these already. Then length is simply the length of the matrix, which means the number of rows. This would be the number of columns, and this is the size. Okay, quick detour into visualizations. Did we get in? No, we didn't do this, I remember. So in MATLAB, when you have to plot some points, you just use plot. Over here you have a list plot. You have a list of points and you display it with list plots. What am I doing here? I'm starting from a function and I'm sampling the function in many points. This is exactly what you would do in MATLAB. And then you show all the points one after another. If you want, you can connect them. That's no problem. But notice that pay attention to the x-axis, the value. It ranges from 1 actually, to what, 500 probably? I'm not sure. Yes, probably it's 500. And it doesn't really tell you where the sign has been evaluated. Why is that? Because this is a list of y values. It's just a list of evaluations of the sine function. If I want to have a corresponding x value, I don't generate just sine of blah, but I say I sine of blah. Okay, so now I have a x and y together. Of course, we don't see anything. Let's do it for many points, and you see that now the range is exactly from -5 to +4. Of course, in Mathematica, it's much easier to do this. You simply pass the function that you want to display. Forget about the sampling, just let Mathematica plot the function for you. And by the way, you can do the same in MATLAB, but the two things are, we would not be comparing apples to apples. I mean, this is what Mathematica is very strong at. So if you have symbolic functions, analytic functions, just use Mathematica for visualizations. If you have data points, MATLAB is for sure better. Over here, I have a lot of operations that you can do on lists, and I will skip all of them because they're actually obvious, they're trivial, and I leave them in the notebook so you can just experiment. You can implement, the thing is that you can implement both list operations and set operations. What is a set operation? Well, if you join two lists, you just put them together. If you use union, it means that you are assuming that these two lists are sets, and when you do the union of two sets, you eliminate the duplicates, and also the ordering doesn't matter anymore. So union removes the duplicates and sorts the list. See that here I have a quick check, and you see that the length of the sum of the lengths will not be the same as the length of the union of the lists. This is because the intersection is non-empty. Okay, all of these we can go very fast. Replace part is to look at one specific element or portion of a list and replace it. And let's get to something that is more important. Flatten is an object that takes a list. Doesn't matter how nested it is, so it doesn't matter how many lists are inside this list. Flatten just splats it out into a into a unique long list. And this is sometimes very useful. Let's see if I get an M. So M is a list and contains other lists, and if I flatten tree form, it shows it, and if I flatten it, you see that we get something like that, flat, and the tree form now doesn't have multiple levels anymore. Okay, let's go to a really important part of this lecture, which is the use of maps and threads, map threads. So here we have our list, and what does map do? Map is a function that takes a function h and a list L, and it applies the function h to each entry of the list. So we started from this list, and now we end up with h applied to each entry of the list. And to understand how map works, it's better to look at the tree form of the list of the input. So we have a list with all of these guys, and map will apply a function to the first level. Or we can specify another integer, the level, and so map can apply to any of these levels. For instance, here I'm telling Mathematica to apply h to the second level of L, which means not up here, but down here. See that these elements are not mapped, but now h appears. And to see what happened, we can do tree form, and you see that all of these guys that were at the second level now went down to the third level because H has been applied to all of them. This means apply to the first two levels. So now we have some expressions to which H has been applied twice, because first level and the second level. All right. Let's see if you guys are smart enough. What's happening here? Map takes a function and a list. So, what is this? It's called a. It's called a. Yeah?
Pure function.
Thank you. It's called a pure function. We have an argument, which is the hash, and then the ampersand. So this is clearly a function, and we will apply it to each entry of L. What does this function do? Yeah?
It calls ground.
What? One?
It calls ground on the argument.
Yes, but it does more than that. In fact, it does much more than that. Yeah?
It returns the two tuple of the argument and the square root of the argument?
Yes, it returns a pair of the argument and its square root. All right. What happens down here? Remember, I'm starting from a list. For each entry of the list, I will replace the entry with another list. So I started from a list, I end up with a matrix. That's why I plot matrix form. I will have a long and skinny matrix. It will have, I don't know how many columns, actually we can count. It will have 2 columns and 3 rows. Let's see. How many columns did I say? 2 columns. Did I say 3 rows? Yeah, 7 rows, of course. All right, a square root of a, 4 square root of 4, and so on. Very good. What will be this output? Now, our pure function is this here, and our input is this. So what does the pure function do? Yeah?
Calculates a function v with the argument of what's given.
Yeah, applies v to the argument. Nothing more than that. What will I get as an output?
A matrix is 1 column. A vector.
Other suggestions?
Oh no.
Matrix with 3 columns.
Matrix with 3 columns. Okay.
List of 2 elements containing a V of the list 1, 2, 3 and a V of the list.
I like this a lot. This looks like a matrix, but really it's a list of 2 lists. So V will be applied to the first list and to the second list. That's it. Because I'm tricky. There is no sense in taking the matrix form. Yeah.
Do we have to use a pure function, or could we just say v? And
Very, very good.
ah,
So his question is, what happens if I do that? And you are absolutely right. We don't need a pure function because we're just applying v, so that's perfectly fine. Now, if we want to do what probably we meant to do before, which is apply v to each entry of the matrix, we have to specify the level. So we have a 2, and now we have what we wanted. we can do crazy stuff like apply V to all the possible levels. Okay, but it's not enough. We can do even better. Okay, this is the same as before. We just see that V is applied at all levels. We can do even better. We can use map all, which on top of applying at each level applies V even to the head, so even to the list itself, even to the symbol list. That's what I mean. Okay, map works on all expressions, not just lists. Why is that? Because I told you that in Mathematica a list is not different than any other expression. Actually, any other expression is not different than a list. If you have the sum of three numbers, this is expressed as plus the three numbers. If you have a function with three arguments, this is just t and the three arguments. And a list, it's just list with three elements. So if we do this, now we have t of v of 23, v of kk, and so on. Okay? And if I map v to a sum of objects, I will just get the sum of the v of each object. And this is what I meant before, heads equal true. This is the same as map all, by the way. Now even t gets the function. Yeah.
What happens if we use map this heads to true on a list? Do we get an t list or something like this?
So you're saying if we do this,
No, heads to true, yes, but not application of
ah,
t, but a list of 23k.
yeah, sure.
Okay.
Mm. Mm. So this is no different than this. Over here, that's V applied to the head already.
What does the heads arrow to mean?
It means that it applies V not just to the element of the function, but also to the head of the function.
Ah,
So-
it's an option.
Yeah, it's an option.
Okay.
And now, okay, now we do some exercises. We start with a random list of numbers, and we want to write a program which for some reason came out already, so I hope you didn't see it. We want to use map to find out if in this list of numbers there is a prime number, one or more prime numbers. So remember maybe 2 weeks ago, last week we were doing everything with replacement rules. Now we do everything with maps. So how to figure out if there is a prime number in this list? Map list. This is for sure. Suggestions?
Does Mathematica have a prime test?
Yes, it does. It's called the prime Q, I think. Is this enough? Should we do something with prime Q or not?
We have to tell, if we do that, we get a list where it's of true and false,
Mm-hmm.
and now we have to check if there's true in the list.
Okay, well, let's start. We got a list with true and false. Fortunately, we do have a prime, but this is not very satisfactory because we don't know which number is actually prime.
Can we use filter?
Can I do what?
Can we use filter?
Filter.
Yeah.
Yeah, we can use filters, but wait. So to answer your question, at this point you can just do OR. And of course it doesn't work. Why not? Or, yeah. I would.
Map or?
No, no, I have to apply OR. Okay. I didn't tell you how to apply, I guess, yet, but this is the apply. Or, okay, if I want to see which number is prime, I can just do the following, right? And I get that 653 is prime. Or, okay, I could filter and select, but not quite yet. I will get there later. I want to see number, okay. Actually, I say to look at select now, so sure, let's look at select. Let's follow my own advice. So, I don't want to do this, that's why I say select is another function that takes a list and a test. And you guys just look at this by yourself, but that's what it does. It just selects the elements in a list that satisfy the test. Okay, now we want to see if there is any number which is divisible by 17. Who helps me with that? Mod, I like mod. Mod is defined for sure. What do we do with mod? Yeah, we do that. Comma 17. Then what? And remember, we need this to complete the function definition. And we have some multiples of 17. And again, if we want to see which numbers, I guess I do it here, we just, well, okay. Now we want to compute the exponential of all of those numbers. This is easy, right? And if I want, again, to see number and its exponential, now we have to do everything. And if I want the numeric value, here we go. Okay, yeah. Okay, about sine of n over n. Same story. These are easy, these are easy. Okay, returning the nth power of the function sine of x. What do I mean? I want to, so the first number is 357, so I want to return the function 357, and then the function sine of x to the power of 453, and so on. So that's what I want to do. How to do that? Okay, is that a function? Let's see. Now we take the second entry. Now we apply 3. There is a problem. My argument 3 is not applied. Do you see the problem? Why would x be, so maybe that's how I should show it. That's what I want, right? I want functions. So this x, certainly not an argument. So how to fix this?
Can we name these parameters? Do we have some kind of scoping?
This is the name. Don't say that. It's like suggesting to invert a matrix. Nope, not happening. This is the name of the arguments.
If you change the x to the power sign, can you have two lists?
Yes, you can have two of those. Let's see what happens.
Well, I mean, can you have comma another list?
No, 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 no. Yeah.
I would put an ampersand before the power operator. Before that. That has to stay. That one. Yeah. Oh, that's nice. I don't know if that is.
Mm-mm.
Now test it again with the second argument getting 3.
Come on, it's not gonna work.
Okay. Parentheses would not make a difference.
No.
So what if you put another bracket
Mm-hmm.
in front of the sign, and then you at the end you put the ampersand?
Mm-hmm. Unfortunately, the brackets by themselves don't do much, but you're on the right way, on the right routes. Why not to do something like this?
And then now at the very end, I think we can put.
So, yeah, okay. First of all, what do we get? We get a list of functions. Oops, wait. Function. Thank you, guys. Why didn't this work? X sine x to the power of. Come on. Okay. So what was the problem here? The fact that we had two arguments to take care of, but only one of them had to be bound to the list, to the entry, and the other one had to stay free. And that's why I used a separate pure function where I specify my argument. So now my x is bound to this guy here. By the way, this is not necessary. Okay. And my hash is bound to the list. Okay, list of functions. What are the functions? Sine, cosine, x cubed minus x, and the integral of whatever between 1 and x. And, okay, not x, the 1 and b, okay? And now we add our list. No, sorry, that's not what I want to do. And now I want to, I want to evaluate all of these four functions in pi. And of course I want to use my map. So, what should be the function here?
Sharp, and then the brackets with pi.
That's it? At least this. So what are we doing? Who complains? Who's happy with this? Anybody complains? This is a list of functions. The hash will pick each of the functions and will apply the function to pi. I'm okay with that. And it works. So now we have the integral from 0 to pi, we have pi cubed to minus pi, and so on. Here's another one. Now I have two lists, and I want to combine them together. And I still want to use map. So I need your help. Hint number 1, map only takes one list. Yeah?
There is a transpose function.
Yes, of course there is. So you know it, but you don't want to say it. All right. Anyone else who sees the solution? You have it?
We have to transpose both lists and put them in a matrix so that each row contains the two values that we want.
That's a good idea, but let me start showing you a problem. This works nicely in MATLAB, and this doesn't work at all in Mathematica. This is actually a real pain in the ass.
But we can first make the...
Yeah, so now I like what you're saying. So, but if you put them together, So, okay, then what do we do with this?
Sharp, and then axis, the first element, with double brackets, yes, and then to the power of sharp and the second element.
Okay. Very nice. So here the trick was to manipulate the lists to generate an object that then it's very easily massaged. Okay, now we have a list of functions and a list of points. And I want to apply sine to x, cosine to y, and so on. Okay, this part I do because you probably figured it out already. How about this part?
So in LF, there are a lot of functions, and in X, there are a lot of arguments, right?
Mm-hmm.
So we make it as we made it before with function. No?
First element, you take the second element as the argument.
And you see how easily we get confused with square brackets here, but it actually works. Sine of x, cosine of y, valuation to 0, okay, and integral. Alrighty. Yes?
Is there a way to turn these two-element lists that are put as arguments such that the function we give gets two arguments and not one list argument?
Yes. I'll get to that very soon, but not quite. Okay, map indexed. That's what you wanted to do before. Now we do have the index. Let's see what it does. So let's see the difference between map and map indexed. Now, map, we simply have a v applied to the arguments. Map indexed, v is applied to the index, to the argument, and it also, out of the blue, an index appears, which is available to v. And this index is the second argument of v. Okay? So now we can use it. For instance, what we did before, I can do with map indexed. Now the argument of v is #1, and #2 is the index. So this, see, #1 will be mapped, will be matched to these guys, and #2 unfortunately gets a list with 1, list with 2. So I not only do I have to take #2, but I have to take the first entry element of #2, and then I get that. If I didn't have this, I would have something strange, okay? So that's what I need. Okay, if I map to a level that is higher than 1, then I have a list of indices. So let's see what happens here. This is level 1, this is level 2. And now if I apply map indexed, see, I have a list of indices. This A, it's in the first list, element 1, B will be first list, element 2, C will be second list, element 1, C, second list, element 1, D, second list, element 2. E is not going to get any V because E is at level 1 and we are mapping at level 2. And now, questions about this? And now to your question, how to use map so that it uses two lists. Okay, you don't use map, you use map thread. And this is when I go wild with my drawing skills. To remember this, what does threading mean? You have this is a blanket, this is another blanket. Then you have a needle with a thread and you go like and you're trying to thread the two blankets together. That's threading in English, and that is map threading. So you're using map to put two lists together. And in fact, this is a really powerful threading or needle or whatever. You can thread not just two lists, but as many as you want, as long as they have the same length. So in this particular case, I have two lists of size 4. Then I'm generating another one still of size 4. So I have 3 lists of size 4. And I can thread them with the function t. So t gets the first entries of each list, then gets the second entry of each list, the third entries, and so on. That's map threading. Map threading is extremely powerful. Okay, apply, that's what I used before with the OR, takes a function and, notice, does not apply the function to all the arguments. No. Takes all the arguments and passes them to the function. So it invokes the function with all the arguments at once. If I want to multiply all the objects together, I pass times to all of these guys. Notice 2 and 4 are put together, okay. What do you think will come out of this?
A list containing 1 plus A, 2 plus B, and 4 plus D.
No. Close, but not quite. Yeah,
One list of 7 and A plus B plus D.
yeah, which is what you said after being evaluated, okay? Because the lists have the same length, so they are added together. What's going to happen here? We will combine these 3 lists. Oh, notice how map thread is invoked. Sorry, forget about map thread. Tell you later. Okay, so over here, that's what join does. It creates a list out of all the lists. So it replaces the list head with join, and so everything is put together. Okay, map and apply have shortcuts. Map is used, it's called like this, and apply is called like this. And if you evaluate them, you see map, shortcut, and apply, same story. Now, notice the differences. Here I apply T to each entry. Here I apply T to the list of entries. Yes, this is just a function invocation. I simply apply T to the list. Here I map. So this is a shortcut. Here I apply. So this is to show that it's very cryptic. You can do a lot of things with very few characters. It's not necessarily a good thing, but you can really do a lot of things. Okay, and here there is a list of other objects that you should look at. Select, I showed you briefly already. Cases, positions. Cases and selects might look like the same. They're not. But if you want, just read the manual. Okay, and after all of this long introduction, I think we deserve to have some fun. And so now we do some real programming. I don't know how long it's going to take, but I want to show you guys how we can compute the Fibonacci sequence, the Fibonacci numbers in Mathematica in many different ways. And I want to evaluate these different ways. So we will time them, and the same type of competition you guys will participate in with the assignment, and in the end, the same way we will determine the winner here. We will have a winner among you guys, not for Fibonacci, but for something else. Okay, first of all, how to time in Mathematica with timing. Timing returns a list with the time as a first entry in seconds, and with the actual result as a second entry. Since most of the times we don't really care about the result, we just want to see how fast we can compute it, you just have to put a semicolon. Okay, see here we are computing 10 to the 4th and 10 to the 5th entries, digits of pi, and this is how long it takes. And by the way, these timers are kind of awful, Okay, in this particular case, there is a reason. We had cached these results. That's why the numbers dropped. But the timers are not very good, as in if you compute the same thing twice, but different objects, so caching cannot be an issue, you still get fluctuations. The same is true for MATLAB. So these are not high accuracy timers. But when we get to seconds or tenths of a second, this is fine. Okay, before I go into Fibonacci, I just wanted to show you that you can use variable assignments in programming in functional languages. The with statement is the way to assign values to a variable so that you don't have, maybe you have to use the variable, this expression 2 or more times in your body, and you don't have every time to build the expression from functions. You can just create it, assign it to a variable like y, and then you use it later on. And if you remember the very first lecture, we were playing with scopes. That's what this is about. So with, we open and we have a list of variable definitions. In this particular case, I have x and y. Then in the body of my with, oh, look at that, I have another with. And by sheer coincidence, I redefine the variable x. Now in the innermost body, I print x and y, and in the outer body, I print x and y. So I'm sure that you guys can guess what comes out. I will have 2 print statements, so tell me what it's going to be printed out, please.
So x will be 1 and 0.
Okay, I agree with that. How about y?
This with function only applies to that local copy of x.
What do you mean it only applies to? The with takes a list of variable names to which you can assign some local, some temporary values.
So I think it first plots 1 and then v of 1 plus v of 2 plus v of 3 plus v of 4,
Mm-hmm.
then plots 0 in the same form.
I think I agree with you. So 1 and 0 as it was predicted before, and then we have v of 1, that's what map does, applies v to all those guys, and then plus adds everything together. And there is no difference where we are. Okay. So how about this? Yeah.
I would say it's x plus 5, because at that point x is not defined yet when we define y.
So somebody wanted x to be evaluated to 4 and then y to become 9. Unfortunately, that doesn't happen. All of these assignments are evaluated in parallel. There is no sequence over there. But if you replace with module, nothing will change. See, that's why I wrote it down. That's why you should use block instead. So there are 3 constructs: with, module, and block. And of course, I never remember which one does what. That's why I put down. Okay, and if you use block, now these guys are executed one after the other. So y now it's 9. Okay, and we will use this in our Fibonacci.
What is the difference? Is there a difference between module and with?
I think so. I think module protects. So in module you can just specify a list of variables to be protected without having to initialize them. And in with you have to initialize them. So it's very, very subtle. Okay, what's the most efficient way? We have 7 different approaches. Let's go through all of them one by one. Recursive, we have seen this already. It's not the most idiotic definition because over here I don't use the delayed assignment, so there is already a little bit of cleverness. So we define it and we time it. Okay. And to get up to 30, it's already in the seconds, and the result is, okay, whatever. We had the discussion already, so I don't have to cover the dynamic programming too much into details. You know what this is like, okay? The base case is the same, and then I have the double function definition. N underscore catches, it's the pattern, and then it says, okay, since I caught this pattern, why don't I just store the result? That's what this part of the definition does. And this is the actual definition. So Fibonacci, dynamic Fibonacci of 20, good. Maybe if I evaluate that. Okay. What are the differences? Fibonacci of R, this is it. Fibonacci dynamic. Now I have all the definitions. Okay. And now Fibonacci of 30, dynamic Fibonacci of 30. Yes, good point. But for now, I just want to show you what it is like. And the point is that now it's super fast because from 30 it has to go down to 20 and not down to 1. Anyway, the result is the same. We will compare all of them later. Now, this is the part that creates some issues with me. Back in the days with Mathematica version 1 and 2, and I believe 3 as well, this implementation would be awful. That's why I loved Mathematica so much, because it really showed that imperative programming was not the way to go. Unfortunately, people kept using Mathematica in a procedural way, and so they optimized instructions like the for loop or the while. So how does for work? It gets 4 arguments. You have some initialization over here. Notice that the arguments are separated by comma, simple comma. So my initialization actually consists of 3 instructions. Then I have a test, then I have an increment, and then I have a body loop body. Okay, what does Fibonacci iterative do? It repeats a loop. So over here we initialize the Fibonacci sequence with 0 and 1, and then we have this very, very nice simultaneous assignment. Let's see what that does. Zero, 1, 1, 2, 3, 5, 8, 13. Let's say that I am at the very beginning. I am T0 is here, T1 is here. This is my window. Now I have this assignment. What does it do? T0 takes T1. So basically T0 now looks at this guy here. And T1 takes T0 plus itself. So adds these 2 guys. So basically looks at the next one. Okay. And then at the next iteration will be always a shift. Okay? Why? Because T0 simply moves 1 to the right and T1 takes itself and the left. Some of you might complain saying, what about the order in which those 2 assignments are assignments are executed? Well, Mathematica has this beautiful simultaneous assignment. So let's say that x equals 5, y equals 7, x. If you use the curly braces, so lists, you can do this. You can do this. everything always works perfectly. So there is no sequencing, okay? This is a real simultaneous assignment. Okay. Fibonacci, iterative Fibonacci of 20 does what it's supposed to be doing. I have a second variant of iterative Fibonacci. This is the traditional way. Basically, I don't trust this simultaneous assignment, and what do? I store my T0, I update T1, and I update T0, and then I overwrite T1 with this with the auxiliary. The result is exactly the same, it's just that I'm not using the Mathematicas functionality. All right, now let's go to symbolic computations. Again, back in the days, this example would work perfectly. Now they are becoming smarter and smarter. In Mathematica, there is a function rsolve for a recurrent solve. Basically, it solves recurrent relations. You can just specify the recurrent definition that defines the Fibonacci sequence, and you can ask Mathematica to solve it analytically. So, what is the definition? We say we have a function or a sequence G. That's what we want to compute. And we say the relation is that g of n equals blah, g of n minus 1 plus g of n minus 2. We also specify some initial conditions. Then we say the function that we want to solve is g, and n is our argument. And you press enter, well, shift enter, and Mathematica would try to spit out an analytical formula for you. Unfortunately, now they got smart and they recognize, oh, that's a Fibonacci, and they have their own function that identifies the Fibonacci sequence, and they have their own way to evaluate the Fibonacci sequence. So now it doesn't work anymore. But had you done this a few years ago, Mathematica would have spat out this thing, would have given you this formula. This is the exact formula to evaluate the nth Fibonacci number. If you replace n with 5, this gives you the 5th Fibonacci number. So we have seen 30 already, we have seen 40 already, 20, 30. I don't think we have seen 1,000 yet. And see how fast it is. Why is it so fast? It's not recursive, it's nothing, there is no loop. It's a direct evaluation of the solution. Okay.
One question.
Yes.
What happens if Mathematica is not able to find a closed-form solution?
It tells you that it's not able, and it returns the equation unevaluated.
Can you override it so that it does spit out the formula instead of the function?
I don't think so. I wish. Let's see. I don't think so. Gives a few. I'm not sure how to do that. I don't think you can do it, because associated with this is not just a sequence. It's a way to evaluate the sequence. It's an algorithm for actually evaluating, and of course they don't disclose that. So I'm not sure if you can. I would have to look it up. I'm not sure. Other questions? Okay. Yes, there is.
Closed form, it will output floating point number?
No, this is an integer. Let me show you for something small.
So it's not enough to compute symbolically.
So let's take this. Let's remove the expand. Okay, that's what it does. Then you can do simplify, and it simplifies it. There is no floating point arithmetic here.
Even, okay.
Okay?
Instead of simplify, could you write n?
Yes, of course I could write n, but that changes everything. Because now we are going into floating point numbers. So we don't have integers anymore. So if it's small enough, let me see. Clear. No, it doesn't expand it.
What makes expand?
That's right. No, if it's 2, it could be expandable. 3, but of course, if it expands it. Ah, okay. So if I don't divide, maybe. Nope, of course not. Okay, forget about that. So, let's continue. The idea of going for n is actually not stupid. So what if we perform the same computation, but now in floating point numbers? So what if we replace all of that with n? So the problem is that we end up not with an integer. Then what should I do? I ask Mathematica to generate as many digits as I know the solution will have. So it takes a little bit of analysis, and I know that the Fibonacci of n has not more than so many digits. So if I ask Mathematica to work with those many digits, I know for sure that I will get an integer. Okay. Notice that if I didn't pass that, then I would not get my integer. I would just get a number with 16 with 16 decimal digits and a big argument and a big exponent. That's it. But that doesn't really give me the right solution, the right result.
What does n over 2 mean in the round?
And divided by 2. I know that this is enough numbers, enough digits, so that the computation, so that the result ends up being an integer. If I pass less than those, I might do this. I might end up in this situation. Where I just get an approximation of the result. But the result is an integer, so I don't want an approximation. I want the exact number. Okay, functional. The same thing that we did for the iterative, we do with the functional. So we have a function next that looks at 2 numbers, and from these 2 numbers generates the next 2. How does it do it? With the standard, with the simultaneous assignment. Basically, x is shifted, x from here now points to the next one, and my y takes my x and y and basically goes there. So that's simply a shift, okay? That's what my next function does. So this is my step. Then I use nest. Nest is a nice little function that takes a function as input, an expression, and how many times I want to apply f to the expression. So what do I want to do? I want to start from the expression. The expression is the initialization, 0, 1, and I want to apply my shift function n minus 1 times. So what does it mean? I initialize next to 0, 1, and I say apply next, basically shift n minus 1 times. That's my functional definition of Fibonacci. This is cool. Compared to iterative programming, this is much cooler. And we get the outputs, okay? Finally, matrix formulation. Let's look at these magic matrices. Okay. 0, 1, 1, 1. This is our magic matrix, and we apply it to this other matrix. And let's assume that this matrix contains Fibonacci number. For instance, A, B, C are A, B, and C are just 3 numbers, one after another. Okay, that's our assumption. What happens when I apply this matrix to A, B, C? Apply, I mean multiply them together. So over here I plot I plot the matrix with the zeros. Here I plot the matrix with the blah blah. And over here multiply them together, and then look at that, replacement rules. Since A and B are Fibonacci number, A plus B is going to be the next Fibonacci number. And same story, B plus C will be the even further one. I don't know why there is a result over here already. I just evaluated it. Okay, so if I apply this matrix to this Fibonacci number, look at that. I get 3 other Fibonacci number. A disappears, B takes a position of A, C takes a position of B, and D appears down here. See? So if I keep applying the matrix 0, 1, 1, 1 from the left to the same matrix, the initial matrix, I actually keep generating Fibonacci numbers. All right, and let's see. So here I define matrix power. That's Mathematica's way of raising a matrix to a power. Here I pass the matrix, and here I pass the power. And then I take the bottom right corner, so this element here. Fibonacci of 20, and returns the right thing. Now we have 10 minutes or 15 minutes to run the tests. So now I clear Fibonacci, dynamic Fibonacci, not to cheat. I redefine Fibonacci dynamic. Then what do? I create a list of my functions. These are all the Fibonaccis I have defined. Recursive, we don't even try, okay? We didn't even put it. Dynamic, iterative 1, iterative 2, symbolic, numeric, functional, and matrix power. Then what do? For each function, I write the name of the function. Here it is. And then I take the time of the function over 1,000. I don't want to see what the output is, and that's why I get this column. Then I flatten, so I get a nice little list over here. And so what it means is that I will have a matrix with the 7 rows and 3 columns. So we evaluated, and I am stupid because I evaluated it twice. So I don't think this... what can we see from this? Symbolic is not doing very well. See, it's the slowest. Numeric is much better. Function is okay. Unfortunately, okay, let me do something here. Definitions. I need to do something. Okay, let's start over. And of course, I forgot that. I had prepared everything in the right order. This one is missing. Okay, once again, let me quit the kernel. I go through all the definitions. Recursion. Okay, so these are good numbers. They're more credible. So it looks like only Fibonacci symbolic is not really working. At least it's kind of slow. And that is absolutely intuitive, because it's not using floating point arithmetic, it's actually carrying out the computation with really large integers, really large integers. So this is for sure a very slow computation. So over here, I want to show you what happens if I execute Fibonacci D with the 10,000. So our evaluation was for the 1,000th Fibonacci number. If I go up to 10,000, Fibonacci D crashes the core, the kernel. It's not the Mathematica crashes, the kernel crashes. So basically it shuts down and I have to reevaluate everything. If you allow me, I skip that part. That's why I put all the definitions back here, because I would have to restart all of them. Okay, and let's proceed evaluating all the other methods except for dynamic Fibonacci, now for 10,000. Let's see if there is a clear loser, and if so, we eliminate it. And it's taking quite long, so there will be a clear loser. So this is obvious, right?
The symbolic Fibonacci was the closed form we saw.
Yeah, the closed form,
Okay.
precisely. No approximation, nothing.
Could we add Mathematica's Fibonacci function to the benchmark?
That's a good point. I hope it works like this. Oh yeah, I should have removed. So symbolic, we don't need it anymore. Let's start simple just to make sure. Okay. Okay. And we were at 10,000, right? Okay. So we want this. I would not be surprised if they were really fast. So I removed the symbolic and I've pushed it 1 order of magnitude up. Look at that. Okay. So iterative is not really working. Functional, much better than iterative. It's twice as fast. Notice also that the simultaneous assignment is better than the swap done by hand. Numeric, it's much better than symbolic, but still not quite. Functional, it's faster than iterative. Matrix power, it's really fast. And then of course they have their own secret code. So what I have down here, I select Fibonacci iterative 1 because it was the fastest of those. Then the functional because it was faster, the matrix, and I pushed to 1 million. Should not be so slow.
The iterative solution probably takes 5 seconds.
Probably. It's very likely that takes 5 seconds. Plus 3, 8 seconds. But 8 seconds are gone already. Did I skip something? Oh, yeah, here we go. Yeah, 5 seconds. Yeah, precisely. So, among our routines, the matrix power is by far the fastest. It's like 2 orders of magnitude, so it's 100 times faster than anything else. And of course, that's why they don't release, they don't disclose what this is. Okay.
So, does Mathematica give almost similar timings on repeated runs? So
0.13 and 0.25. Okay. This means caching. This thing was cached clearly. Okay, this is very big. Okay. So 2 and 4. Let's repeat it. See? So they use caching a lot. Okay, guys, questions?
Why is the matrix version the best one?
Well, because this is a very, very smart matrix. It only has zeros and ones. You're not really doing floating point arithmetic. It's just a matter of shifting. The only operation you're performing is an addition. I think this is super fast. Yeah.
There's something else going on. Matrix exponentiation can be done in log n.
Oh yeah, of course, that too. That's right. Yes.
So just matrix exponentiation dot any. You just pull out if it's an odd exponent, you pull out 1. And if it's even, you split it in 2. Then you just do a square.
Yeah, it's a logarithm. It's a logarithm approach. From n, you go down to the power of n over 2, and then you just keep going down. So the tree has a depth of log n. So yes, this is of course very fast. That's right. And on top of that, there is no floating point number. This is just one addition, super fast. Everything else is just a shifting, so no problem. Okay, guys, I will see you on Thursday.